Good morning. All right, let's get started on our second half of week, what is it, 3 on atoms and elements. So last night we talked about some of the basics of atomic structure, the different particles, whether they have mass or a charge, and a little bit of an intro to the periodic table. So today we're going to talk a little bit more about isotopes and ions and fill in some of the blanks that we left last time. If you haven't had a chance to try this out, we're not going to go through every single thing, but when we get to the part at the end when we're filling in the table, if you haven't had a chance to try that yet, maybe just leave the stream at that point, as much as I hate to say that because I love having you here, but just so you have a chance to try it on your own before you see me, or watch a couple examples and then try it on your own. All right, so let's take a look at where we stopped last time, looking at these models of atoms that now contain all these different particles, a nucleus, and then electrons around the outside, and then they're also paired with their symbols. You can see the symbols here, and we're going to try to make some meaning out of that. What do those things mean? So the best way to do that is just to look for similarities and differences. We did that last night when we talked about the what it means for them to all have the same name. And let's look at some of the other things that are going on here. So first of all, we can see now that we have enough significant figures. We can see that electrons do indeed have mass. So for example, hydrogen with one electron has a mass of 1.0078 AMU. Hydrogen, when it loses that electron, has the mass of 1.0073 AMU. So when we get all the way into those 10,000ths place, that's when the electron mass starts to matter. But anything, 3 decimal places or before, it really doesn't affect it that much, depending on the number of electrons. We can see the same thing kind of down here. We also see now there are some other differences in there as well, because of some of the very, very slight differences in AMUs with protons and neutrons. But generally, like even if you look at the periodic table, with their average masses, we're not seeing that. And it looks like my internet is cutting out again. So I'm just going to wait and see if it comes back. All right, looks like it's back. So the stream will catch up a little bit. Probably won't be live exactly for a minute, but I think it's okay. All right. So let's talk about isotopes. Isotopes, as you can see here, are particles where, it says down here actually, H1, H2, H3 are isotopes of hydrogen, carbon-12 and carbon-13 are isotopes of carbon. And that's when they have different numbers of neutrons. So the same type of atom, carbon, carbon, hydrogen, 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 can have different masses. And those different masses are caused by different numbers of neutrons. They can't have different numbers of protons. So you'll notice all the hydrogens have 1 proton, all the carbons have 6, all the magnesiums have 12. Because if they had different numbers of protons, then it would be a different atom. And some of the questions below address that. So for example, how many protons are in all chlorine atoms? Let's look here at number 26. So we look up chlorine on the periodic table, and you can see it's right up here, number 17. And so all chlorine atoms must have 17 protons. Do chlorine atoms exist with 18 protons? They do not. And why not? Because any atom that had 18 protons is no longer called chlorine. It is now argon, the next one over. So that's no longer chlorine. That is now argon. All right. So now let's start looking at the charges. So the little pluses and minuses that we see here. Back to our model here. So we can see when hydrogen gets a plus, you can see now that it is missing an electron compared to the others. Carbon here has a minus, and if we count those electrons, we see there's 6, 6, and 7. So there's an additional electron in carbon minus. And then magnesium has an ion form over here of +2. And if we count that, you'll see that it has 10 electrons instead of 12 in these others. All right, so something about the number of electrons controls that plus or minus charge. And that kind of makes sense because we know protons are positively charged. So if there's an equal number of protons and electrons, like in the hydrogen atom here, and these carbon and magnesium, if there's an equal number of protons and electrons, then we have a neutral overall charge, so 0 charge, because you have as much plus as you have minus. If you have more electrons, now you're adding negatively charged things, so the overall charge of that particle is now going to be negative, and that's what we see here. We have one more electron than protons, so that one becomes negative. And then when we have fewer electrons than protons, now we have something that is positively charged because the positively charged protons outnumber the negatively charged electrons. So 12 protons, 10 electrons leads to a +2 charge overall of that particle. And so we call that an ion. All right. So for reasons that we'll talk about later when we get into electron configurations, some particles or some atoms always make the same type of ion. So they either always lose the same number of electrons or always gain the same number of electrons to make the same type of ion. So for example, all of the alkali metals here in this column all make +1 ions. So however many electrons they started with, they can lose 1 electron and become a +1 ion. The next column over, +2. Now in the middle, it gets kind of messy. You can see some of these have 2 different ones. Some of them just have 1, but it's not necessarily predictable. So we usually don't worry too much about those in terms of predicting the charges, the ions that they'll form. And then when we move back over to the nonmetals, we have predictability again. So we have aluminum, which is always +3. Carbon is it does make a different sort of an ion. I don't want to, that one's less reliable. But then these columns, we can reliably see -3, -2, and -1 ions. Now, sometimes those are written with the number first, so like 3-, 2-. Sometimes they're written with the charge first, -3, -2. Means the same thing. The number first is a little bit more standard because that way it's less confusing. So if you have -2 and then you have some other thing next to it, it's not necessarily clear if that 2 corresponds to the minus or the thing that's next to it. So this way it's very clear that that applies to just that atom. But either way you want to write it is fine. All right, so then overall we can have this type of a symbol where A is our, I think it's, yeah, here. X is the element symbol, right, the thing from the periodic table. If there's a little number on the upper left, that is the mass number. So that's the protons and the neutrons. If there's a number down in the lower left-hand corner, that's usually the atomic number. But remember, that's kind of redundant because we know that the atomic number and the element symbol always go together. So if it has a atomic, or if it has an element symbol, we don't need the atomic number, but sometimes it's given just for clarity. And then in the upper right is where you see the overall charge. So that's going to be the protons minus the electrons. And if there's nothing written there, we assume it's 0. And when it is 0, we usually don't write the 0 there. We just leave it off. Okay, so with that, we should be ready now to complete our table. Now I want to bring your attention to a couple things first that we, just to avoid confusion. So atomic number, we talked about that. Mass number, we talked about that. Average atomic mass, we did not talk about. And this is what you see on the periodic table. So if you look at these little numbers like underneath the atoms here, that's the average atomic mass, and that is different from the mass number. That's not the sum of the protons and the neutrons. That is the average of all the different isotopes, the weighted average of the different isotopes that exist on Earth for that element. So for example, if we look up at carbon, it says 12.011. There are no carbon atoms with a mass of 12.011. What there are atoms that are carbon 12, atoms that are carbon 13, and some that are carbon 14. So 3 different isotopes of carbon exist. The vast majority of that, about 99%, is carbon 12. There's some carbon 13 and then a very small amount of carbon 14. So by weighting those averages, you get the overall kind of average mass as 12.011. But that's not the mass of any single particle. So we can't ever use these numbers to determine the numbers of protons and neutrons and things like that in our atom. Those are average masses. We'll use those for some calculations when we're dealing with lots of them at the same time, and we'll get into that in a later chapter. But for now, we can't really get much information from those numbers. So we put them on this table just because of that issue, because we don't want to be confused by that. So for example, sulfur, and all the numbers are shown here on this one. So we've got atomic number of 16, we've got a mass number of 33, and we've got a charge of -2. So let's go through how we get all the rest of the table filled out from that symbol. So the atomic number, that's easy. We can either just get it from the lower left if it's given, or we look it up on the periodic table. The mass number, again, that kind of has to be given here because we can't get that from the periodic table. The average atomic mass we do get from the periodic table, but we can't really do anything else with it. So we just write it down. The net charge we have here from our symbol, -2, and it's an anion. There are 2 types of ions. Positive charged ions are called cations, and negatively charged ions are called anions. And then we can calculate our numbers of subatomic particles. So 16 protons, we get that from the atomic number of 16. 17 neutrons, we get that because the neutrons and the protons together have to be the mass number, so protons plus neutrons. So if we've got 16 protons, we must have 17 neutrons to have a 33 mass overall. And then our number of electrons, we look at the charge, and we say, okay, well, if it's -2 charge, that means there has to be 2 more electrons than protons. So we had 16 protons, we must have 18 electrons. All right, let's try the next one. We'll do the next 2 rows together, and then I'll let you figure out the rest on your own. So here we have a symbol of 40K. Notice a couple things different from the sulfur one. For one, the atomic number is not given. For another, there's no charge. Now, the atomic number not being given is fine because we can just look up K. If there's no charge, that means we have to assume that the charge is actually 0. So this is a neutral particle. All right, so let's start looking this stuff up. We got to find our atomic number. So from that, we need a periodic table. We can find K way over there on the left, and that is number 19. So atomic number of 19. The mass number, remember, we don't get that from the periodic table. We get that from the symbol. So it's given here as 40. So we just write down 40 here. And then the average atomic mass we can look up. And in this case, oh, that's really small. Hold on. Looks like 39.098. Our net charge is 0 because no charge is given here. All right, so now let's start calculating our numbers of subatomic particles. We've got 19 protons. We've got, to get our neutrons, we need whatever number gets us to 40 because the mass number is the protons and the neutrons together. So that makes 21 neutrons. And then the number of electrons, well, we have a net charge of 0. So that tells us that we need the same number of protons and electrons. So 19 protons, 19 electrons. That's it. All right, we'll do one more. This time, the next row down, we don't have any symbol given. we're given the numbers of particles, and we're going to work backwards to the symbol. So let's get our information from the particles. 15 protons means an atomic number of 15, because those always go together. We can get our mass number by adding up the protons and the neutrons. So 15 protons and 17 neutrons, 15 plus 17 is 32. So our mass number must be 32. The average atomic mass we can't get yet because we don't know which element we are dealing with. The net charge we can, because we know protons and we know electrons. So 15 protons, 18 electrons. That's telling me there are 3 more electrons. Electrons are negatively charged, so our overall charge is -3, and that's an anion. More electrons than protons. All right, let's finish this up then. So we have an atomic number of 15. So we can look up element number 15, and it is right here, phosphorus. Our mass number is 32, so we'll put that up in the upper left. If you want, you can put a 15 down in the lower left, like in the sulfur one, but you don't have to because we know that the element is phosphorus. And then our charge is -3, so we're going to put a 3 minus up in the upper right. The only thing we have left to fill in then is our average atomic mass, which again, these are hard for me to read on my screen. Looks like 30.974. Might not be right. Okay. And that's how you do that. So just some other things as you're going down here. You'll notice this zinc, the next one down, it doesn't have a mass number given on the upper left, and that's because it's actually given here. So just you can fill that in that way. And hopefully you can do the rest of those columns. And that'll give you, put you in good shape for completing the rest of this. Oh, thanks for adding the mass for me. I appreciate it. All right. So I actually, that's it. This is a kind of a short unit. Let me know if you have any questions, or if as you start filling these things in, if you're not sure. I think what I'm going to do at the end of the video here, I'm going to fill this out and then just have it up there. But please don't copy me right away. Go ahead and leave, pause the video, and I will do this. And then when you're done with your table, you can come back and check it. All right. So I'll say goodbye for now. I'll see half of you in a couple hours on campus, and the rest of you online next Monday evening. So bye, everybody. And now I'm going to do the rest of the table for you. We got 30. You can find these from the periodic table, so I'm not going to bother filling those in. This is a +2, so that makes it a cation. Our atomic number is 30. Our number of neutrons is 8, which is not realistic, but that's fine. I'm going to double check that. And then our number of electrons must be 28. All right, over here, we've got 35, 81. Let's do all our particles first, and then we can fill in the symbol. So neutrons, 35. We got 81 mass number overall. So that's going to be 46 neutrons. 35 protons, 36 electrons gives us a -1. And I believe this is bromine. Uranium, I believe, is 92. Yep. So that's 92 protons and 143 neutrons. Neutral charge means 92 electrons. Chlorine is 9. Oh, sorry, that one has a negative. I didn't see it. So 9 protons, 11 neutrons, and then 10 electrons. One extra electron for the -1 charge. And then just you can copy these numbers from the periodic table. All right, I hope you got all those right. See you next time.